Hi folks, welcome back to this next lesson in the P4 topic, which I'll be honest with you, I've forgotten what number this is now, but this is all to do with fission and nuclear power. Okay, so we're gonna touch on fission today, and we're gonna go into a little bit more detail about fission next lesson when we compare it to something else. So fission and nuclear power is what I want you to be interested in today. I want you to describe how nuclear power stations use fission. There's three outcomes that I want you to be able to do by the end of the video lesson. Number one is describe what fission is. Number two, describe the structure of a nuclear power station. And then number three, I want you to explain the benefits and drawbacks of nuclear power. So if by the end of this lesson, if you just rewind back to this point and you have a look at these 3 points here, if you can't do any of them, go and do some extra research till you get yourself to the point where you do understand each of these 3 points. Okay, you need to be ticking these outcomes off as you're going along, basically. There's some keywords: control rods, graphite moderators, chain reaction, daughter nuclei. Don't worry if you don't know what any of those mean, because what we're going to do today. There's 3 questions there I want you to try and have a go at. So just pause the video, just spend like 60 seconds on each one and see what you remember from previous lessons. So just pause the video, give those 3 questions a go now. Okay, let's go through those then. So what are the 3 main types of ionizing radiation? So the 3 main types, the 3 that we've been discussing, are alpha decay, beta decay and gamma decay. Those are the 3 main types of ionizing radiation that we're interested in. Describe what the half-life of a radioactive substance is. Right, so half-life is just the time it takes for half of all the radioactive nuclei in a substance to decay. So if you've got a specific number, let's say 1,000,000, the half-life of that substance will be the time it takes for 500,000 of them to decay and give out radiation. So you've only got 500,000 radioactive unstable nuclei left. That's the half-life. And it's just measured in time. That's all half-life is. Why are some nuclei unstable? You should have said for that one is due to their mass. They've got lots of energy, usually because they've got lots of mass. So the bigger and bigger you get in terms of a nuclei, the more energy it's got, and therefore the more unstable it becomes. So that's why you look on the periodic table, and the ones with the lowest mass, like hydrogen, helium, and you're going along on the top rows, they're all fairly stable. None of those are radioactive. And it's just because, well, they're quite small. And because they're quite small, the mass is quite small. Because the mass is quite small, they've not got a lot of energy, and therefore they're not unstable. You get towards the bottom of the periodic table, where the masses are getting enormous, you get a lot of energy with those because the mass is enormous, and therefore they're quite unstable. Okay, so that's why some nuclei are unstable. Okay, so this is a question, but I'm just going to tell you the answer straight away. So what are the 2 ways in which we can obtain energy from atoms? Well, there's 2 ways, and that is fission or fusion. Okay, so fusion we're going to do more about next lesson, but this lesson we're just really focusing on fission. But I'm going to describe just very briefly what each of those 2 things means, well, right now, basically. So fission is the splitting up of atomic nuclei. You can see I've got a nucleus there, and then it's broken up into 2 smaller nuclei. We call these daughter nuclei, but we'll go through that in a second. I don't know why they're daughter and not son or whatever, child nuclei. It just means 2 smaller than the original one. And then fusion is, well, the exact opposite of that, and it's not a physics word really. Fusion can be used in other ways. You know, if you fuse 2 things together, that's exactly what we mean. So fusion is the fusing together of atomic nuclei. You can see I've taken 2 smaller nuclei here and I've combined them together into a larger one. Both of these processes release energy, okay? And we'll compare them in the next lesson probably. So when a neutron collides with an atom of uranium-235, it splits into 2 daughter nuclei and releases some neutrons. So hopefully what you're looking at here is, well, nothing new really. We've got a nuclei here and we're given the letter U, and again, if you've got your periodic table out, you'll know that U stands for uranium, and it's got a mass of 235, so it's got a big mass, so it's fairly unstable already, and it's got an atomic number of 92, meaning it's got 92 protons. Now what we can do is, if we get a lump of uranium and we fire a neutron at it, that neutron will be absorbed by a nuclei of uranium. And when it does that, guess what? Its mass goes up a little bit and it becomes even more unstable. It becomes so unstable it actually breaks apart, okay? And we end up with these 2 smaller nuclei, and some other things get released as well. But before we get 3 neutrons being released here, you can see, so I've got 1 nuclei that's smaller than that, I've got another nuclei that's smaller than that, and I've got 3 neutrons. Also, energy is released, and this is the stuff that we're interested in. Energy gets released. But I just want to point something out to you that's really important here. If I add up the mass before this arrow, so before the reaction took place, let's add up the mass. 235 and 1 is 236. So before anything happened, the total mass on this side was 236. If you add up the mass on this side, 91 plus 142 plus 1, 2, 3, because each of these neutrons has got a mass of 1 as well, guess what? You end up with a mass of 236. The mass before and the mass after is the same. Okay, so this is a fission reaction. You start off with an atom of uranium which absorbs a neutron. It becomes super unstable and breaks apart into two daughter nuclei. Now they're smaller than the original uranium-235 atom. It gives out 3 neutrons as well. They fly off, and it also gives out some energy. That is fission. That isn't the end of this story though. So if you're in a nuclear power station and it's a uranium-powered nuclear power station, and this happens, which is what you want to happen, you want it to split up and give out energy. That's the whole point of nuclear power. But you can notice these 3 things here, 3 little neutrons, they've just gone flying off. This whole process started with a neutron being absorbed by a uranium nuclei. Now if you've got a lump of nuclear fuel, as in enriched uranium, enriched just means it's got more uranium nuclei in it than would naturally be found. Okay, so it's kind of enriched to make sure there's lots and lots of fuel in each of the lumps of nuclear fuel in the power station. These 3 neutrons are going to fly off, and guess what they're going to be absorbed by? Yeah, more uranium nuclei. So then each one of those would break up into daughter nuclei, and then they'd give out 3 neutrons as well. So we call this process where you start off the process with 1, and it kicks out some neutrons in the whole fission splitting up process. It kicks out some neutrons. Those neutrons get absorbed by other uranium nuclei. They then break up into daughter nuclei and more neutrons, and you can see how this would quickly get out of control. Okay, this is called a chain reaction, and they can quickly run out of control. Really important to stress here. This uranium nuclei broke up, and in this case it happened to make krypton and barium. It doesn't need to make krypton and barium. It could literally make any 2 daughter nuclei, as long as if you add up all the mass it's the same as this. Okay, so for example this might have actually had a atomic number of 35, and this might have had an atomic number of 56. So let me just grab up my periodic table just to show you what I'm actually on about there. Where is it? There. So my point being here, it doesn't have to be krypton and barium it makes. In fact, frequently it'll make something else. I just want you to know that the mass before and the mass after is the same, and as long as the masses add up before and after, those 2 daughter nuclei that it makes could be completely different. So for example, instead of 36, let's say it made something that had an atomic number of 35. So it might have made bromine there. So that could be bromine. And this, instead of 56, it could have been lanthanum. So it might have made bromine and lanthanum instead. But if you add up the masses of bromine and lanthanum and the atomic numbers and everything else, the mass would have stayed the same. So the daughter nuclei are always exactly the same. The camera's a bit wobbly there, I don't know why. Hopefully that's better. Okay then, so let's move on. So if you wanted to summarise this, because obviously if I want you to remember fission, I don't want you to write all this cool beans out, but we could summarise it into one example nuclear equation, alright? So here's an example nuclear equation for fission, and it just shows you that if you take 1 neutron, and I know it's a neutron because it says down here there's a letter N, which gives it away already, but it's got a mass of 1, alright, but it's got an atomic number of 0. But the only subatomic particle that's got mass but doesn't have a proton involved, that isn't a proton, is a neutron. So you take a neutron and you combine it with a uranium nucleus, you get a nuclear reaction happening. In this case it's going to be fission, and it splits up into 2 smaller nuclei, and this is really handy because it actually shows you that it is smaller than that. You end up with 2 smaller nuclei and you end up with 3 neutrons. It also has plus energy. Energy is released in the form of gamma rays in this situation. So there is a nuclear equation. If you're making notes as you're going through these video lessons, that's quite an important one to get down if you're going to be making notes. Okay, so that is the idea that uranium-235 can split up, thanks to nuclear fission, into smaller daughter nuclei, and it will release 3 extra neutrons, and it will also release some energy. And that energy we can then use to heat water, which will then turn into steam and everything else. We're going to show you a power station next. Right, this is a power station. I don't know if you've seen a power station before or seen how a power station works. It doesn't matter if it's gas, coal, wood, nuclear. They all essentially work the same way. The only thing that changes is the fuel, basically. So what actually gets water hot. So I'm gonna start here. You can kind of ignore this whole like control rods and all that gubbins for now. I'm going to go through that in more detail in a second. But the idea is I've got some nuclear fuel in this reactor core here, this reactor vessel, and giving out energy means it gets hot. And as it gets hot, you can see that the heat, thanks to the heat exchanger, goes into this water and it heats the water up. And just like in your kitchen, if you heat water up, it will make steam. So the water gets hot in here, it turns into steam, and it goes through a turbine. And a turbine, just think of it like a massive big fan, essentially. And if you pass steam over that, it's going to make the turbine spin. Now if I've got a spinning turbine and I manage to attach that to a generator, I've just made myself electricity. Electricity is just something that takes kinetic energy and turns it into electrical. So far I've had nuclear fuel that is undergoing fission, producing heat. The heat heats water, the water turns into steam, the steam turns a turbine, the turbine turns a generator, electricity gets produced. But what's pretty interesting is that steam that passed over the turbine is then sent through a condenser, and this here, you can see that the water that's cooling this steam down, is completely separate. It's in different pipes, and the reason we do that is in case this was to become radioactive, we don't want to just start spilling water outside that's radioactive, so we keep it completely separate. Okay, so this acts a bit like a little cooler, and the water will be this water where it says to reservoir, that can go outside because that's not actually been inside the reactor vessel. There's no chance of that being radioactive. So it cools the steam down, the steam condenses, and then it gets pumped back into the reactor vessel, and it gets heated up again, turns into steam, and you can see this just keeps going round and round and round. Okay, this is completely separate to this. This is completely separate to this. Okay, it's pipe work essentially where heat gets transferred from one to the other. Okay, so if you want to pause that and have a quick look at it and try and figure out what's going on there, that's fine by me. It looks really confusing, but if you just pick one point and just work your way around it, it does kind of make sense. Okay, so that is a nuclear power station. If this was a gas power station, all of this would look exactly the same, but this wouldn't be a reactor vessel there, it'd just be gas burners that are heating water into steam. If this was coal, none of this would be it, it'd just be coal being burnt to produce heat, to heat this water into steam. Everything else would be the same. Okay, you still got a turbine, still got a generator, still got a condenser, and it all gets pumped back into the system again. Okay, so the only difference is the source of heat. So let's have a look at that reactor vessel in a bit more detail then. So this, again, looks dead confusing to start off with, but if you chunk it up, it does make sense. Okay, so to maintain a safe level of chain reaction, steps are taken to control the fission reactions. I should stress this doesn't always work. So there has been nuclear disasters like at Chernobyl where it was the chain reaction basically went out of control. It couldn't be controlled any longer, partly due to ineptitude of the nuclear technicians that were working that night, but also partly due to a design flaw in that nuclear reactor vessel that they were using. But in a normal nuclear reactor vessel, this is the kind of thing that you need to remember and the thing that's used. Okay, so a graphite core or moderator reduces how much each fuel rod can interact with another. So let's just have a quick look at this. This here is graphite core. Anything grey, that is as well, that is as well, that is as well. So the fuel rods sit inside graphite cores, or as they're called, graphite moderators as well sometimes, and that tries to prevent them from interacting with each other too much, to try and keep a lid on it a little bit. Okay. On top of that, we also have these things here. You can see it says movable control rod, and the control rods are movable. They can be moved up and down, and you can appreciate that if I move this control rod up now, there's very little between this rod of nuclear fuel and this rod of nuclear fuel. So neutrons from here will be able to fire over to that one, neutrons from here will be able to fire over to that one, and it'll cause the chain reaction to happen. So at the start, if your reactor's like offline, like no fission is taking place, if you lift all the control rods up, then neutrons start flying from one to the other, and the reaction starts, and they start making more heat and more heat and more heat. Well, that's carefully monitored, and then if the heat starts to get too high, the control rods start to drop down and reduce that fission so it doesn't get too hot. That's what a meltdown is, if you've ever heard the word meltdown before. So these control rods are constantly moved up and down just by small amounts, just to try and keep the level of fission reaction at a manageable rate. Because if it got out of control, there's not much you can do there, and that is basically what happened at Chernobyl. Again, if you've not watched, don't know about Chernobyl, or you've not watched, there was a really good TV series, was it last year, I think, on Sky, that's worth watching. Might be HBO actually, but it did a really good job of covering what happened and the aftermath of it especially, so definitely worth a watch. Right, so there's some problems associated with nuclear power, and I've just picked like the 4 big ones that I want to go through with you. So the first one is meltdowns. Now if you speak to someone about nuclear power, if I was to say to you, oh, do you want me to build a nuclear power station near your house? The answer is usually going to be no, and this is the big reason in people's minds, okay? So an uncontrolled chain reaction could lead to a nuclear meltdown. No one wants to be around a nuclear power station that's going through a meltdown, okay? That is going to have a disastrous effect. So meltdowns are one of the big problems associated with nuclear power. I should also point out though that these are incredibly uncommon, okay? The chances of this happening are very, very tiny, but still people have this kind of stigma attached to it, and they don't want to near it basically. A commissioning cost is another drawback, okay? So actually setting up a nuclear power station and getting hold of nuclear fuel is bloody expensive. So commissioning cost is again one of the drawbacks. Disposal of radioactive material. If you run a nuclear power station and you've got fuel rods, and that's great, eventually those fuel rods become less and less effective, because as you know from Half-Life, the Half-Life lesson that we did, over time it will become more and more stable, and therefore it'll give out less and less neutrons, and it won't produce as much energy because it's not as radioactive as it used to be. So eventually you need to take those fuel rods out and dispose of them. That's a problem. and it's a problem for a few reasons. One, the half-life is usually like ridiculous, really long half-lives. It's toxic, it's radioactive, so the methods that they use to actually dispose of this are pretty insane. So first of all, you'll never find it on like a boat or anything like that. They use trains to dispose of nuclear waste just because they are less likely to be involved in an accident, so they won't stick them in a lorry or anything like that. They go on trains. They're taken to somewhere where they can be buried incredibly deep below the ground. But before that happens, they put the spent nuclear fuel rods in barrels, fill the barrels with concrete. They put the barrels inside shipping containers, or the big metal shipping containers, they fill that with concrete. And then they take that shipping container down underground and they store them there. That is, at the minute, the only thing that we can do with spent nuclear fuel is literally just bury it and hope that it never gets uncovered. Apparently, there are places where nuclear fuel's been buried and they've had to put signs up in the past saying, don't dig here because there's some, it's dangerous. And there's been like the risk of people going and digging it up. It's ridiculous. So that's another thing that needs to be factored into it. Also, another thing that's not really thought of too much is what about earthquakes? So what happens if you've got this sealed chamber with all this nuclear waste in, and there's an earthquake and that sealed chamber is no longer sealed? That needs to be considered. Right, we talked about commissioning cost, but there's also a decommissioning cost, which is arguably going to be costing more than it did to build the power station in the first place. Okay, so when a nuclear power station needs to be shut down, the removal and disposal of potentially radioactive materials is expensive. So it's expensive to bring all that stuff into the power station to build it, like the materials that are used to build it. But then after the fact, those materials might be radioactive. So a ridiculous amount of care needs to be taken to make sure that that doesn't pose a threat to anyone. So actually getting rid of nuclear power stations costs more than building them in the first place. Okay, so that's called the decommissioning cost. Let's have a quick look at these then. So there's 6 comments there, all related to nuclear power. I just want you to pause the video and think, is that a benefit of nuclear power or is it a drawback? Okay, so 6 there. It's either a good thing or a bad thing. So just pause the video and have a quick look at those and see if you can work out what the benefits and drawbacks are. Okay then, so the first one here, reduces the use of fossil fuels. Well, that's a benefit, isn't it? Okay, so if we can reduce our addiction, if you like, to fossil fuels, that can only be a good thing. There's a risk of uncontrolled chain reactions. Hopefully you put that down as a drawback, because obviously if we've got an uncontrolled chain reaction happening, that might lead to a meltdown. Meltdowns, not good for anyone. It produces long-lasting radioactive waste. I don't know anyone that would think of that as a benefit. That is definitely a drawback. Obviously we've not got many things that we could do to dispose of that, apart from the method I described to you a second ago. They're cheap to run once built. That's a benefit, yeah. So once you've actually got it set up, it's expensive to start, but once it's started, pretty cheap to run. You don't have to build it, do you? It's there already, so you're just maintaining whatever was already built, so it's pretty cheap to run once built. It's expensive to build new power stations. That is a drawback, obviously. So if you're having to build a nuclear power station, it's going to cost a lot of money. And then one of the big benefits, no greenhouse gases are produced. So when people talk about nuclear power, if I said to you, name a drawback of nuclear power, a lot of people would say, pollution. They don't create pollution. They don't create greenhouse gases, at least. I mean, nuclear waste, I suppose you could class as pollution if it was actually released into the environment, but it's not. It's all stored. So no greenhouse gases are produced, and pollution is the wrong word to use in an exam question. Don't write the word pollution for nuclear power because it's not involved, essentially. Nuclear waste, fair enough, talk about that, but not pollution. Okay, that's not the same thing. Right, so I want you to have a go at some questions now. I don't mind if you rewind the video to help you out with this. I don't mind if you go and have a bit of research. I don't care how you do it, basically. But there are a couple of questions on there. How many marks is it out of? 7. Okay, so if you want to spend about 7 minutes on that, that's fine by me. Just pause the video now, give those questions a go, and I'll come back to you with the answers in a second. Okay, let's go through those. So there's the answers to start off with. I'll just read through the questions and go through them though. Nuclear power can be used to generate electricity through nuclear fission, and figure 1 shows the process of nuclear fission. So we've got a uranium-235 ion. This is a neutron here, and it's absorbing the neutron, this uranium-235 ion. It's splitting up into 2 smaller daughter nuclei and emitting 3 neutrons as well. What's not shown here is the fact that it's also produced some energy. Okay. During the process of nuclear fission, a uranium, and you should have had nucleus there, as it says there, absorbs and it's a neutron. Okay, so the word neutron's in that one. Electromagnetic radiation is released in the form of, and you should have said gamma rays. Okay, so that is the 3 words there. So that was nucleus, neutron, and gamma rays. It's got to be in that order. Each one of those is worth 1 mark. Question 1b. The UK needs at least 25 million kilowatts of electrical power at any time. A nuclear power station has an electrical power output of 2,400,000 kilowatts. Calculate how many nuclear power stations are needed to provide 25 million kilowatts of electrical power. Well, to work that out, it's 25 million divided by 2,400,000. Okay, so that'd give you an answer of 10.4. You can't have 0.4 of a nuclear power station, so you're going to have to round that up to 11. Okay, if you've got 11, then that's 2 marks. If you've got 10.4, that's just 1 mark. Okay, so 11 is worth 2 marks, 10.4 is just worth 1. Because you did the right thing calculating 10.4, but you've not realised you can't have a 0.4 of a nuclear power station, so you can't get that second mark. Right, question C. State 2 environmental issues caused by generating electricity using nuclear power stations. So there's a few you could choose from here. Okay, so waste is radioactive, or you might have just said nuclear waste. That's worth a mark. The waste has got a long half-life, or you might say the waste remains dangerous for a long time. Give yourself a mark if you've got that. The waste is toxic. The waste needs to be buried, or it's difficult to dispose of. So any of those two could be given a mark. There's a risk of catastrophic events, and it says here allow named accidents. So if you've specifically named a time when nuclear power, there's been a nuclear incident essentially. So for example, like Fukushima, which is in Japan, Chernobyl, 3 Mile Island. If you've mentioned any of those, you can get the mark there. You might have also said the fuel is non-renewable. Now, it's a bit weird this, because although that is technically correct, the fuel lasts a ridiculously long amount of time. Okay, so yeah, it is non-renewable, but it is something that is fairly abundant as it is, and it lasts a long time. So it's one of the better non-renewable fuels, if that makes sense. We don't really want to be burning oil and coal and everything else, but because once it's gone, it's gone. But nuclear fuel, I should say, lasts quite a long time. Okay, you burn a piece of coal, it's going to burn for not very long. You use a piece of nuclear fuel, it's going to last ages. So, but those are the marks you could have got from that. So if you just add those up and give yourself a mark, what I want you to do now is, I want you to rewind to the start of the video, and I want you to have a look at those 3 outcomes. Can you do all those 3 outcomes? If you can't, I want you to go and do some extra research yourself, make some notes, watch a video, bite size, I don't care how you do it, but those 3 outcomes, they're important that you understand those 3 outcomes in terms of this lesson, and then that will all build into the bigger picture. I think that's it. Yeah, oh, there's a nice little animation of a fission taking place there. You can see it starts off with a large uranium nucleus, absorbs a neutron, splits up into 2 daughter nuclei, and 3 neutrons get emitted as well. So that's fission there in a nice little animation. Hopefully that's been useful. If you've got any questions, ask them in Google Classroom, or ask me, and we'll get back to you. But I think that's going to be it for this one. See you later.